Okay, so we continue to discuss the chapter 4. So today we're going to discuss chapter 4, section 2, contour integral. So assume you first we have a smooth curve. Okay, so we have a smooth curve. It's determined by gamma, and this smooth curve has a neighborhood, and the function f of z is defined over this open neighborhood. Then what we can do, we do the following. We divide the curve into several subcurves, and it's like partition. So this is alpha, this is beta. Alpha is equal to z0, and then you get z1, z2, z3, z4, z5. Let me write z7, z8. Here the final one is z9. Z9 is equal to beta, so you get a partition. And when you have a partition, you measure the arc length between zk minus 1 and zk, not the distance in the complex plane. Its arc length is denoted by delta zk. Okay, so that's the arc length. So it's the length along the curve. And the maximum arc length for each subcurve is called the mesh of the partition. It's a mesh of the partition, and is denoted by this mu of partition P. Here, this is a partition P. Okay, and you have z1, z2, z3, all these steps, and the Riemann integral, you can pick up sample point from each sub-arc. Okay, so you possibly have C1 in the first sub-arc, C2 in the second sub-arc, and so on. And then we choose CK from the arc ZK minus 1, ZK. So the arc, not the straight segment. And define S of P to be FC1, F evaluated at C1 and times delta X. Delta X1 and plus FC2 delta X2 and FCN delta Xn. So just add all these things together. SP is called the Riemann sum of F with respect to the partition P. Okay, so that's the Riemann sum of the function with respect to the partition P. Okay, and then we have the similar definition like the calculus. We're talking about the integral along the curve gamma. Okay, so definition 3. Let f be a complex valued function. Defined on the directed smooth curve. Gamma. And we say that f is integrable along gamma if there exists a complex number L that is the limit of every sequence of Riemann sum SP1, SP2, SPn. Here n means how many cutting point contained in this partition, and sequence, infinite sequence, corresponding to any sequence of partition of gamma satisfying the limit n approaches infinity, the mesh of Pn is 0, i.e. the limit of Riemann sum as Pn as n approach infinity is equal to L whenever the limit n approaching infinity, the mesh of Pn is the limit of the mesh of Pn, mu of Pn is equal to 0. Okay, so this is the integrable, the definition of an integrable function. F is integrable along the gamma. Okay, whenever such L exists, then we say F is integrable. And this is the definition, the complete definition. L is called the integral of F along gamma. Okay, the integral of F along gamma. We write L equal to the limit approaching infinity, the Riemann sum FCK delta ZK, and we write like FZDZ along gamma, FZDZ along gamma, or just directly write the integral of F along gamma. Okay, so that's the similar definition for the Riemann sum, Riemann integral. Okay. So whenever you have a partition, so first of all, partition should be should have a smaller and smaller mesh. Second, this limit does not depend on the choice of a sample point. The sample point, whatever choice of sample point, you will have the same limit L. If this can happen, then the function is integrable. So, okay. And this definition is very, very close to the definition of the Riemann integral in the calculus. So it shares a similar property like the properties First, if fg are integrable along gamma, then f plus or minus g is integrable along gamma, and we have this quantitative result. The integral of f plus g is integral of f plus integral of g, and integral of f minus g is integral of f minus integral of g. Okay, so the additivity, the linear structure, sorry, not additivity, linear structure about the function. And second, if f is integrable, you have a scalar multiplication. Then you can move this scalar multiplication forward. Okay, and property 3. Remember here our gamma is directed. Gamma is from alpha to beta. If you reverse the direction, you get the opposite direction. That is called the negative gamma. So the integral of f along the negative gamma, it just simply changes the direction. It is equal to negative integral of f along the original gamma. Okay, so that's the familiar definition. So here it means that you integrate from a to b or you integrate from b to a. The difference is a negative sign. Okay, so the definition is very complex and tedious. It's very long. It has a lot of requirement. But like the real calculus, we have the affirmative statement about the continuous function. So if f is continuous on the directed smooth curve, then f is integrable along gamma. So this is a very weak condition and very strong result. We don't need any differentiability or whatever, just continuity. When you have a continuous function, it is always integrable along the gamma. Okay. So continuity implies the integrability. This gamma is arbitrary smooth curve. So far we are talking about the smooth curve. Arbitrary, but this smooth curve may not be really just random. It could be just horizontal line, right? The x, the segment in the real axis. So if okay, so the theorem we are not going to prove it. We will not prove it. If gamma is equal to AB, so the gamma is a real interval, then we write the integral of f along gamma equal to the integral of f from A to B. Of course, when we write this way, we mean the direction is from A to B, so we don't mean the other direction. So that's why we write from A to B. It's already directed. This is directed. In this case, you see, f is f of z, so the integral is integral of f of z dz along gamma. But this moment, z is a real number, so it is integral from a to b ft dt. We use the real numbers to represent it. Okay, so ft dt, it's a complex valued real function. It depends on the real variable. So for the complex valued real function, here ft is a complex number, so it's a ut plus ivt, ut plus ivt. Okay, the real part, the imaginary part, and then the integral of ft dt from a to b becomes the integral from a to b ut dt plus I times integral from a to b vt dt. Okay, so just two parts. We already applied that linear structure and the scalar multiplication. Each part, this is a real calculus. This is a real calculus. So the clear theorem will be the following: if the complex valued function f is continuous on the interval AB, and assume it has a derivative f prime of t, capital F prime of t is equal to f of t for all t in AB, then capital F prime of t is little f of t. So it means the derivative of the real part is u, the derivative imaginary part of v. And u, v are real variable functions, so you can apply the fundamental theorem of calculus from the calculus. So you evaluate based on the antiderivative, and to put them together, we have the same fundamental theorem of calculus. So the integral of ft dt from a to b is equal to capital Fb minus capital Fa. Okay, so this is this comes from our original the general complex case, but you can apply it, and you can apply the real calculus fundamental theorem of calculus and cover the complex version. So this is complex valued. It's a complex valued or complex version of a fundamental theorem of calculus, second part. Okay. Let's see the example. We try to compute the integral from 0 to pi e to it dt. E to it dt. Okay, so based on our theorem, we will not prove the theorem. This class is the introduction class, so we will just take for granted many theorems. We will skip the real proof. If you want the proof, you have to take the graduate course about complex analysis. There you will see all the proofs, no skip. Okay, so here we are looking for the antiderivative of EIT. Remember, the antiderivative EIT is EIT over I. For whatever k here, EKT has antiderivative EKT over k. Okay. So you find antiderivative, you're going to evaluate at 0 and pi, and okay, let's continue. It's 1 over I is a coefficient. So e to I pi minus e to I 0. Okay. E to I pi, the argument is a pi, so it's negative 1. E to 0, the argument is 0, is a positive 1. So it's negative 2 over I. You move this I up, so you will get 2I. Cancel with this negative. Okay, so here, we have like the common sense, because when we talk about a real a complex number, z is always a plus bi. So when you have this z equal to negative 2 over I, of course this is a number, but from this number you don't see the real and the imaginary part. It's a complex number. It is a complex number, but you don't see the real and the imaginary part. So that's why we always make the denominator real. So we always multiply top and bottom by I to make the denominator real. We multiply, and this is I squared is negative 1. Cancel with negative 1, you get 2I. And when we have this formula, we see, okay, this complex number has 0 as the real part, 2 as the imaginary part. Okay, So it doesn't mean I cannot be the denominator. It just means when you have the I in the denominator part, you don't see the real and the imaginary part directly. Okay. Okay, so now let's see how do we apply what we just learned to evaluate the stuff. Because you see here, originally the integral of f along along gamma has complex variable. It has complex. When we have complex variable, we cannot apply the fundamental theorem calculus because fundamental theorem calculus require the real variable. The reason we do the previous discussion is because when we have such a thing, this is a real variable, real valued, real variable. Then this u and v are real valued, real variable. Then we can apply the fundamental theorem calculus. But this moment, they are complex values, so you cannot apply the fundamental theorem calculus. But here we assume gamma is smooth. Gamma is smooth. Let's study the definition of this Riemann integral. The Riemann integral starts from the Riemann sum. The Riemann sum is sigma fck delta zk, k from 1 to n. Okay. If we have a smooth curve, then delta zk, the difference is almost the derivative at a certain point and times the difference of k. Because you see here, we consider gamma as a z of t, and t is between a and b. So delta z is approximated by the derivative and times delta t. Okay, the difference is approximated by the derivative times the difference of the input. Okay, so when you realize this, you're going to replace this delta zk by z prime. So Sp is, the Riemann sum is fck, and this part is a z prime of tk delta t. Okay, and c is a complex function, a complex point on the curve. So ck could be z of like tk prime. Ck could be z prime, z times this is a zk minus 1. This is a zk. So c is a z of a tk prime. So let's continue this. It is equal to f of z of tk prime. I use prime because here I have another tk. And z prime of tk and delta tk. So this is the Riemann sum. And then you are going to let the mesh approach 0. When you let mesh approach 0, this give us the equality. Okay, so that's the theorem 4. So how do we get the equality? Equality, what is the equality? So when you pass it to the limit, the sigma becomes integral fz of t, z prime of t. Delta is a differential dt from a to b. So that's the formula. Okay, so we get this type of correspondence from the real calculus. Okay, so the theorem 4 says let f be a function continuous on the directed smooth curve directed smooth curve gamma. Then if z is z of t, the parameterization, t is between a and b, is any admissible parameterization of gamma consistent with its direction, then we have what? We have the integral of f z dz along gamma is equal to the integral from a to b f z of t, z prime of t, and dt. Okay, so that's the explanation or the translation from complex variable to the real variable. If you have a smooth curve, from complex variable to the real variable. We like a real variable because we already have the fundamental theorem of calculus. If we can find the antiderivative of f of z of t times z prime of t, then you can use the fundamental theorem of calculus to evaluate. Okay, so that's the purpose for the theorem 4. Okay. So we want the real variable instead of complex. And in this theorem, you actually have a selection. You say z of t is any admissible. It means you may have more than one admissible parameterization. If you have two admissible parameterization, you will have the same integral. Choose one admissible parameterization, you get the integral f along gamma. Choose another admissible parameterization, you will still get the integral of f along gamma. Okay, so it does not depend on the selection of this admissible parameterization. So that's the corollary one. It's a direct corollary from the theorem. So corollary 1. Corollary 1 says if f is continuous on the directed smooth curve gamma, and if z is equal to z1 of t between a and b, and z is z2 of t is between c d, any two admissible parameterization of gamma consistent with its direction, then the integral from a to b f z1 t z1 prime of t dt. This is one computation for the Riemann integral along the complex curve gamma. It is equal to the integral from c to d f z2 t z2 prime of t dt. Okay, so it's because they are both equal to the original integral, so of course they equal to each other, right? Okay, so here we again say that you just select one admissible parameterization. That's enough. You don't have to say, okay, for this one we compute it, for another one we compute another one. So if you want to confirm, of course, you can try 1 or 2 examples, but that's enough. You only try one, it's enough. Okay, so let's just do some computation. The simplest computation will be the power function. Okay, so compute the integral z minus z0 to nth power along the circle CR, where n is an integer and CR is the circle z minus z0 equal to R traversed once in the counterclockwise direction. Okay, so this z0 is really extra, the useless part. So you just let z0 be 0, then you can simplify, but whatever. So the CR is this one. This is CR with the direction counterclockwise. This is z0, the center. The radius is R. Once means you just get a complete circle. That's enough. So that's where the once. Once, yes, once. Okay, so we choose compute solution. Let z of t be, okay, whenever you have a circle centered at z0 with radius r, you can always write like this. R, EIT. Okay, so the circle is always a center plus radius times EIT. Here this t is between 0 and 2 pi. Okay, so this gave us counterclockwise orientation. It is counterclockwise orientation. If you want clockwise orientation, if you want it this way, you will choose, if you want clockwise orientation, you will choose z of t equal to z0 plus re negative it. Okay, negative it means you change the direction. So it's a small difference. One is positive it, one is a negative it. Okay. 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 Now we have the path zt. Then the z prime of t. Z prime of t is a derivative about t, so it's just r I e I t. Z0 is a constant. The derivative is 0. So this is z prime of t. Then the integral of z minus z0 to nth power dz along gamma. And z, of course, z minus z0. Z minus z0 is REIT. Z minus z0 REIT. And then z minus z0 to nth power becomes r to n e I n t. Okay. R to n e to INT. So this is f of z of t, f of z of t, and times z prime of t. Z prime is r R-I-E-I-T. R-I-E-I-T. This is z prime. N times dt. Okay? Okay, so I is a constant, R is a constant. You can move this forward. So it's R to n plus 1. R to n, R is R to n plus 1 times I, integral from 0 to 2 pi e to I n plus 1 and t dt. Okay, so we simplify it. We get I times n plus 1 times t. Okay, now we have cases. Case 1. N plus 1 is 0. If n plus 1 is 0, this numerator, this power is 0. Power 0, e to 0 is 1. So the integral is n plus 1 is 0, so it's r to 0 times I, then times integral and dt. Okay, this is 0. If you want, I can write this way. So e to 0 dt. This is 1. Integral from 0 to 2 pi of 1 is 2 pi, so it's a 2 pi I. This is a case when n is equal to when n is equal to negative 1. So this is okay. When n plus 1 is not 0, when n plus 1 is not 0, then ein plus 1t has an antiderivative ein plus 1t over I times n plus 1. This is one antiderivative. We're going to use this to do the evaluation. Okay, so the integral z minus z0 to nth power dz along gamma is, so here, we start here. We'll start from here. It's Rn plus 1 I, the antiderivative, and ein plus 1 t from 0 to 2 pi. From 0 to 2 pi. Okay, so I cancelled. So you have r to n plus 1 over n plus 1. E to n plus 1, 2 pi I. You let t be 2 pi, e to n plus 1, 2 pi I, minus e to, when t is 0, 0. Well, e to 0 is 1. This is 1. And we know that the exponential function, complex exponential function is a periodic function. This is, unfortunately, this is also 1. So 1 minus 1 is 0, so the difference is 0. So the integral, when n plus 1 is not equal to 0, the integral is equal to 0. Okay? So we finish this computation. It's just step-by-step computation. Okay, so if we summarize it, we will have the following stuff. The integral along CR, z minus z0 to nth power dz, it is equal to 0 if n is not equal to negative 1. It is equal to 2 pi I if n is equal to negative 1. Okay? Okay, so this gave us like the first idea about the integral along a real curve in the complex plane, not just AB interval. And this is a smooth curve. If we connect the smooth curve, we will get a contour. Remember, contour means a piecewise smooth curve. So, definition 4. Suppose that capital gamma is a contour consisting of the directed smooth curves gamma 1, gamma 2, gamma n. So you have several curves. You have this, 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 this. Okay, if you want to get gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. Okay, it's not necessarily closed, just a piecewise smooth. Okay, and let f be a function continuous on gamma, then the contour integral of f along gamma is denoted by the symbol f along gamma, the same notation, fz dz, and is defined by the equation. What is the equation? Fz dz along gamma is just f along gamma 1 plus f along gamma 2, f along gamma here, n. Okay, so just add them. You integrate the function part by part, piece by piece. Okay, so this is a contour integral of f along the contour gamma. If this contour is just a single point, okay, the special case, if this contour is just a point, then we get, or we set the integral of fz dz, we always set the integral over 1.0. Okay, in our continuous sense. Okay. In this natural sense, there are some other integral. There are some other definition. Certain function is very crazy. Then the integral over 1 point is not 0. That's a different story. It's not what we are trying to study. Okay. Okay. Now let's see one example. Let's see one example. So example 3. First, let's get the contour. The contour is this. This is gamma 1, gamma 2, gamma 3. It's also closed, but it doesn't matter. It's not necessarily closed. It's just a part by part smooth curve. Okay, so this is contour gamma, capital gamma. It's counterclockwise, and we're trying to integrate 1 over z minus. We're trying to integrate. My bad. We're trying to integrate the z bar squared dz along gamma. Z bar squared dz along gamma. We only can assume it's a continuous function. We never assume it's an analytic function. So we can use z bar. It's not a problem. And first of all, this integral, you just write it like z bar squared dz over gamma 1, z bar squared dz over gamma 2, and z bar squared dz over gamma 3. Okay, so this is a 1, 2, 3. We are going to compute part by part. Okay, for gamma 1 is from 0 to 2. So z of t is just t. t is between 0 to 2. Okay? Z of t is is between 0 to 2. Then this integral dz. Here, then z prime, what is a z prime? Z prime of t is 1, so you don't see it. And z bar of t is just t, because t is a real number. The complex conjugate is itself. So integral from 0 to 2, z bar is t squared. Z prime is 1, and dz is z prime times dt, so you get t squared dt. Okay? And t squared antiderivative 1/3 t cubed from 0 to 3. I'm sorry, to 2. My bad. From 0 to 2. 1t is 2 is 8 over 3. 1t is 0 is 0. So we computed the first part. It's just 8 over 3. Right? It's a simple real calculus. It's real. And over gamma 2. Gamma 2 is vertical. Z of t is I times t from 0 plus 2. I times t plus 2. The real part is always 2. Complex part is from 0 to 2. So t is between 0 and 2. Okay? So this is a it plus 2, or 2 plus it. I forgot this 2. And z prime is I. Z prime is I. Then z bar of t is 2 minus it. This is z. Z bar is 2 minus it. Then z bar squared is 2 minus it squared. 2 minus it squared. What is 2 minus it squared? It is 4 minus 4it and minus t squared. Okay? 4 minus 4it and minus t squared. Right? Okay, let's just do the integral. Okay. The integral is gamma 2 z bar squared dz is from 0 to 2 4 minus 4it and minus t squared, and times I and dt. Okay, so I is a constant, so we move I forward. So we get integral 0 4 minus 4it minus t cubed, t squared dt. And we find antiderivative. So 4t minus 2it squared minus 1 over 3 t cubed. Okay, from 0 to pi. From 0 to 2. Am I right? Let's see if we get the right answer. I check with the textbook. My computation is not that correct, it looks. Okay, whatever, let's try to compute. So when t is 2, you get 8 minus 2 squared is 4 times it's 8i minus 8 over 3. When t is 0 is 0. Okay. Why I get different answer? There's a no, there's a positive. That's right. Okay. Okay, so what's this? It's 8. So 8 minus 8 over 3 is 16 over 3 times I. And here is plus 8. So it's 8 plus 16 over 3 times I. Okay, so this is the integral along the second curve. Okay, let's continue this. We get the integral along the third curve. So the integral of z bar gamma 3. Gamma 3 is, where's gamma 3? Gamma 3 is here. From 2 plus 2i to 0. So z of t is initial point plus t times terminal minus initial, 0 minus 2 plus 2i. Okay, so that's always the case. You have initial and terminal minus initial and times t. That's a straight segment, directed segment. Okay, then we simplify it. It's 1 minus t times 2 plus 2i. 1 minus t times 2 plus 2i. Then z prime of t is negative 2 plus 2i. And z bar of t is 1 minus t, 2 minus 2i. 1 minus t, 2 minus 2i. Okay, so we can square that. Z bar of t squared is 1 minus t squared, 2 minus 2i squared. And we integrate of z bar squared dz along gamma 3 is going to be integral from 0 to 1. T is from 0 to 1. This function, 2 minus 2i squared, 1 minus t squared, and times negative 2 plus 2i, and dt. This is constant number. This is constant number. You move it forward. Move them forward. And you integrate 0, 1, 1 minus t squared dt. Okay? So, let's see what this is. Antiderivative. Antiderivative is negative 3, 1 minus t cubed. Negative 3, 1 minus t cubed from 0 to 1. This is a plus b, a minus b is a square minus b square. So it's a negative 2 minus 2i. Then it is 4 plus 4 is 8. Okay, here you 1 t is equal to 1 is 0. 1 t is equal to 0, it's negative 3. So it's positive. Negative 1 over 3. 4 plus 4 is 8. So negative 8 over 3, 2 minus 2i. Okay? Sorry. Negative 8 over 3, 2 minus 2i. So here this is positive, but at the beginning there's negative sign. Okay, so when you have those three numbers, three evaluations, you're going to add them. So the integral of f along the contour is equal to first integral, 8 over 3. Second one, plus 8, 16 over 3i. Third one, minus 8 over 3, 2 minus 2i. Okay, well, whatever. If we do the computation correctly, this is just a number. Okay, so we're not going to verify it's wrong or right. If you want, you can do the verification. Okay, so this is the integral. If we can find the derivative, find the antiderivative, and we have this integral f along gamma equal to the parameterization, admissible parameterization f zt, z prime of t dt. Okay, so that's the computation for this formula. Okay, so we still have some topic. We will discuss it next time. Okay, we stop here today. And For this one, for this part, you can try the evaluation of, for example, on page 122. On page 122, you can try the exercise 3. You can try to evaluate exercise 5, 3, 5, and 6, and 7. Yes. So we just do the computation. We just try the computation. 122, page 122, 3, 5, 6, and 7. Okay? Okay, great. Thank you. We'll stop here today.